Okay, this is Dr. Eads, and I'm your instructor for Physics 253 this semester. So this is the very first in what's going to be hopefully a whole bunch of videos that just has some basic information on the text that you need to watch before you get to class. So starting right at the beginning, so a little bit on introduction and what exactly is physics. So this is covering chapters 1-1 and 1-2 in the textbook. So on to the second slide. So what exactly is physics? So many of you have probably taken physics before, or at least heard of physics, but physics is a natural, or what's also called a physical science. That means we're interested in the natural world, the things that are all around us. So it's experimental, which means that we do experiments, we make observations, we collect data, and then we actually test our predictions based on those experiments and based on those observations. So another way to think of it, it's really what physicists do is they study matter and energy. So matter is the stuff that makes everything up, and energy tells you how that stuff interacts with itself. So basically everything in the universe is made up of matter and energy. So another way to think of it is that physics is the study of everything. So, and I think the simplest way to think about it is really the goal of physics, and my goal as a physicist, is to understand the fundamental laws that govern the world around us, right? So we want to explain how things work and why things work. Okay, so your textbook covers a whole lot of physics. And so first off, so the first part, and this is actually what we're going to be spending almost all of our time on this semester, is classical mechanics. So classical mechanics is all about how and why things move. So this is Physics 253, which is this course. So then it gets into fluids and thermodynamics. So you could think of this as really advanced applications of classical mechanics, because fluids, again, it's all about things moving, but it's a little more complicated since it's a fluid and not just individual particles, and same thing with thermodynamics. So we will get a little into fluids this semester in Physics 253, so we will not, however, get into thermodynamics. So, and then next up is electricity. So static electricity and electric charge. So this is in Physics 273, which will be the next semester of general physics. And then magnetism. And of course, magnetism and electricity are actually related to each other, which is known as electromagnetism. So this is also covered in Physics 253. So finally, then you move on to light and radiation, which is covered in the third semester of the general physics sequence. So this is Physics 283, and all you electrical engineering majors will have to take the third semester, so the mechanical engineers are not required to, but hey, if you want to take it, why not? It's interesting. And then it also gets into modern physics. And, modern is kind of an interesting term in physics because basically it's sort of everything about 1900, so over 100 years at this point, but we still call it modern. And this is special relativity, quantum mechanics, nuclear physics, atomic physics, and cosmology. And this is also, the basics of this is also covered in Physics 283. Okay, so finally the process of science, so how science is done, and this is just some terminology that the textbook uses that I wanted to make sure you're aware of. So first off, everything is based on these principles. So in a principle, it really governs some property or behavior of the physical universe. And then there's also, somewhat confusingly, this term called a law, which typically you see a law is a well-tested principle that's been around forever and has all sorts of experimental evidence. But typically in your textbook actually sort of uses these interchangeably, right? It's not like there's some master committee that in fact decides when a principle becomes a law. It's just sort of one of these things that just kind of happens. Not only that, sort of a lot of the time, you think of a principle as having some sort of a limitation. For example, Newton's laws. So Newton's laws tell you about motion, and we know that Newton's laws don't always work. In fact, if you get speeds very, very close to the speed of light, Newton's laws don't work anymore, but they're still called Newton's laws, even though we know they only have limited applicability, just simply because they've been along forever, and once something becomes a law, typically you don't demote it back to a principle. So another one of the key points are these things about concepts. So a concept is an idea that makes it possible to describe the physical world clearly. So for example, the idea that things are made up of atoms, right? So this is a concept, and it actually allows you to make all sorts of interesting predictions about the natural world. Another thing is the concept of a force. So Newton's laws and Newtonian mechanics are based on this idea of forces, which are pushes and pulls. And this is inherent, and it's a concept that's really fundamental, and it gives you a way to describe how objects move. So, of course, we're scientists, so we have these things called scientific theories, and a scientific theory makes a testable prediction. And of course, as scientists, we go off and test these predictions with experiments, right? So we perform these experiments that collect evidence that can either refute or support a theory. So incidentally, you never really prove a theory, right? You can only refute things, but as time goes on and you collect more and more evidence to support a theory, then it becomes, you're more and more sure that it's actually a good description of the world around us.